everyone, Katrina here, and today I'm going to tell you all about equivalent trig expressions and why this is an important trig identity. Be sure to subscribe for more videos like these. Okay, so we always hear about sine functions and cos functions, but in reality, they're almost the exact same thing. They're just simply shifted 1/4 period away from each other. So we're going to prove this mathematically today, and I'm going to show you a really neat identity that you can derive from this phenomenon. So first of all, I'm going to draw your attention to this triangle that I have over here. So we can see that, first of all, this is a right angle triangle. Okay, so that means we have a right angle triangle, which is 90 degrees, and we can use this information to find the other angles in our triangle. So as soon as you have a right angle triangle, you're able to use SOH CAH TOA. So this helps us define the relationship between the adjacent side, the opposite side, and the hypotenuse with respect to our angle theta. So in my previous videos, I talk a lot about trigonometric ratios and how you can use them to solve trigonometric equations. So be sure to check out that if you need a bit more information there. So we're going to use some of that information today. So first of all, we can see that here sine theta equals to opposite over hypotenuse, and we've got that cos theta equals to adjacent over hypotenuse. So looking at our triangle here, let's see what that means for us. Okay, so let's do this in orange. So let's start with sine. So sine A. So our theta here, we're going to start with A, which is angle A, which is representative of our theta, and this equals to opposite over hypotenuse. So our opposite is side length lowercase a over our hypotenuse or our radius here, which is lowercase c. What about cosine? So we can see cosine of b. So we're now looking at this angle over here equals to as well. It equals to adjacent over hypotenuse, which is also a over c. Okay, so what do we see here? Well, we've just shown that sine A equals to cos B. So let's write that out once more. So what have we discovered? Therefore, sine A equals to cos B. How can this help us? So let's try to define what is our angle sine as rewriting it as cos. So we want to look first at the angle here. So we know that this is sine A. Okay, so let's just write that out. So we have that sine A, which is the same as sine theta. What is that equal to? Well, we can see that this equals to cos of pi over 2 minus theta. How did we get that? So we can see that this is a right angle triangle. So if it's a right angle triangle, that means this angle over here is pi over 2 or 90 degrees. And this angle over here is theta. So then what about this angle B over here? So we can represent this angle B simply as pi over 2 minus theta. We've derived one trig identity or a equivalent trigonometric expression. Another way to look at it is in terms of transformations, how you would have your negative theta essentially and then plus pi over 2. So why don't I show you what that means? So if we rewrite this in terms of transformations, we can have it as cos, and then we have negative pi plus pi over 2. Remember, we always have to factor out the negative here, so it would be cos negative and then theta minus pi over 2, which means that we are moving our function pi over 2 to the right. And pi over 2 is 1/4 period of sine and cosine functions. So this shows, like I said earlier, that sine and cos are simply 1/4 shift away from each other. Okay, so let's do a bit of an example to explain that. So for this example, let's consider sine pi over 5. And what we want to do, we want to have an equivalent trig expression for this in terms of cosine. So what did we learn previously? We stated that sine theta equals to cos pi over 2 minus theta. And you have to understand that this theta and this theta, it's the same thing. If we look back up at our plot over here, that's this theta over here. That is our angle A in terms of this triangle. So what does that mean? So for this example, we know that theta equals to pi over 5. So to find an equivalent expression, all we have to do is have pi over 2 minus pi over 5 to create the total internal angle for a cos. So we've got pi over 2 minus pi over 5, because we see that our theta here is pi over 5, right? So what is pi over 2 minus pi over 5? Let's go ahead and find a common denominator, which is 10. So we'd have 5 pi minus 2 pi over 10, because first I'm multiplying the top and bottom here by 5. Then I'm multiplying the top and bottom for the second one by 2, which gives me my result here. And 5 pi minus 2 pi equals to 3 pi, and this is all over 10. So therefore, I would say that sine pi over 5 equals to cos 3 pi over 10. So we were able to rewrite this in terms of another trigonometric ratio, which is really cool. Because sometimes when we're trying to prove identities or graph certain things or solve trigonometric equations, it's sometimes easier to actually see a function as another function instead. It might be easier to find that angle, or maybe just easier to visualize a different representation. So it's always good to understand, I guess, that relationship between your trigonometric functions and understand when they are equivalent or not. So I'm going to give you a couple more neat equivalent expressions. And this one is going to rely on symmetry and even and odd functions. So let's start off with sine theta. So sine theta is an odd function. So since it's an odd function, that means that it has point symmetry about the origin. So about the origin. And what is the origin? That is 0.00. So I do cover some of this information about even and odd functions in my even and odd function video, but now you can see its relationship to trigonometry. So what does that mean for us today? So since sine is an odd function and it has point symmetry about the origin, that also means, so point symmetry about the origin means that you can rotate your function 180 degrees or pi radians and end up where you started. This also means that you can reflect across the x-axis and across the y-axis to end up to what you started with. So in terms of an equivalent trigonometric identity, this actually gives us information about our transformations. So in particular, if we were to have sine of negative theta, this is equivalent to negative sine of theta. So that's actually really cool. So you can take kind of this horizontal reflection and you can put it to the front as a vertical reflection, and this does not change the function. This is also due to its periodic nature, which is really neat. So it has to do because it's an odd function, and also has to do because it's a periodic function. So this is a really great identity or equivalent expression for you to know. Let's move on and do the same thing, but instead for cosine. So let's look at cos theta, for example. So if sine theta was an odd function, do you have any thought about what cos theta could be? So cos theta is in fact an even function. So even functions have symmetry, and in particular, they have line symmetry. So they have line symmetry about the line x equals to 0. So that is the same as the y-axis. So you can reflect it over the y-axis and it can be the same. So what does that mean in terms of an expression? So that means that you can take cos negative theta, and that's the same as cos theta. Because what this tells us is This is a reflection over the y-axis, a horizontal reflection, and if you reflect over the y-axis, you end up with the same function. So if you think about the cos function, it looks like this. If we were to continue it over its period, it would look like that. So you can see right away here that it has this line of symmetry down the y-axis, so that if you were to reflect it back and forth over this axis, your function would remain unchanged, and that's why we can have this extra identity here that cos of negative theta simply just equals to cos theta. So this is really great when you're trying to simplify problems. You can essentially have that negative disappear, and then you're just dealing with the positive angle. So always be sure to take note of these equivalent trig expressions when you're working on solving trigonometric equations, as well as when you're trying to prove trigonometric identities. And with that, I will let you do some practice, and I will see you in my next video. Please subscribe if you're enjoying these videos, and definitely give it a like. I'll see you next time.